right, so we have our final speaker, which is Tanisha, and she'll tell us about quantum machine learning.
Okay, hi, so I'm Tanisha. Interesting story. I'm still in high school, so my last year of high school. And for the past year, I got super interested in learning about what quantum computing was. So I guess I went through my own sort of learning curve, trying to understand this really complex area. And then I read about this course starting at UofT on Twitter, and I learned that Professor Henry was hosting it. So then I ended up coming into his class one day and then just sticking around. So I decided to get the most out of this experience, being in a class and learning about this. I wanted to do a project as well, so I picked the area of quantum machine learning. So I hope I can teach you guys something interesting today. Okay. So anabolic steroids basically help muscle cells make more protein so that each cell can work more powerfully, more efficiently, and can grow really, really big. Basically giving it the superpower to be more efficient and just work at a faster rate and grow a lot faster. So when I think about quantum computing, I think of quantum computers being sort of the steroids for machine learning, where you have quantum computers making machine learning algorithms a lot faster, efficient, and more powerful. Hopefully, that's what we think, without any of the negative side effects. So I wanted to realize, why is this field of research even important? And as we can know, a huge specified area where you can conduct this research is in drug discovery or material discovery, where this problem is too complex to compute or understand on classical computers. So maybe the potential of using quantum machine learning, the intersection of these two technologies, could help solve these really, really big problems. And why do you even want to work on this specific problem is this drug discovery alone by 2025 will be around $71 billion as their market share. And it's probably going to become introduce material discovery and various innovations that can slide off of these areas. So it's a huge marketplace where a lot of innovation can still be done. And if you think about it, the efficiency of making one drug to solve a specific problem, it takes 12 years, I think, to just come up with one specific drug for a disease. Super inefficient. So definitely an area where you can use technologies like quantum machine learning to provide a better solution or a better way to approach this problem. So when I looked into the research, I ended up looking into a specific machine learning classifier called distance-based classifiers. And before getting into what it is, the output that I got was, what is the efficiency of when you input and this was done on the iris data set, so the flower data set, where it just takes two features of the images, and if you take the input vectors and put it in, can it classify it correctly and with accuracy? So the first result is the actual probability of it achieving proper accuracy. So it's not really good with the triangle is the experimental, and the asterisk is the theoretical of what the probability should be when this input vector is input into the classifier and what the accuracy should be. So it's not very good, and this is probably due to the fact that when it was implemented on the IBM circuit, there's still lack of error correction and coherence time that interferes with it working efficiently. However, it was still able to classify each input as class 0, which is the output that you want to achieve, correctly. So it did do its job, just not very efficiently. But the classifier works. So then I inputted the same thing on a Python terminal, and it got relatively the same sort of efficiency. At the end, both input vectors, when inputted into the classifier, were correctly classified at state 0. And when I actually ran this again as a computational basis on the IBM Q experience, I actually got terrible results. So this one doesn't correspond at all with what it should be. It gave me the probability of state 1, but I think that sums up to it being just still a noisy system, and the coherence time is probably affecting that as well. So I can look in more into it, but the results are still interesting. learning because the first two experimental results gave you the right output. And so how do you approach quantum machine learning? So most methods are is the idea of taking a machine learning model and translating it into a quantum circuit. However, this becomes super inefficient for hardware right now because a lot of these complex machine learning algorithms probably require a lot of gates, and then this increases the coherence time you need for your qubits to stay, to compute through all this, and then it ends up being really, really inefficient. So an opposite approach to this is how can you take a quantum circuit that's optimal and be able to do classification on it? And this is a distance-based classifier. So it's super simple. You only have a Hadamard gate and two measurement gates after you do your state preparation. And so the first step will be your data pre-processing, and this is very prevalent in how most classical machine learning works. You take your raw data set, you standardize it to your zero mean and unit variance, so all your data is converged into the center, and then you normalize it so it stays within the range of -1 and 1, where your first class could be -1, and then your second class could be +1, for the two different types of classes you can have for this specific data set. And after that, you want to be able to actually start encoding this data set into the quantum computer. So the way to do that is you encode the input vectors as an amplitude, and this is a scheme of how you would do it. You have 4 registers. The first register is like the nth register that takes in all and flags in all the training inputs. The second one is the ancilla, which is entangled with the third register, and then you have your last register, which basically it was a 1 qubit, which either if it is in state 0, the classification related to it will be -1. If it's in state 1, it'll be classified, the output will be classified as +1. So after that is done, you apply, so that's your state preparation, then you apply your Hadamard gate to the ancilla qubit, so you can entangle or interfere the second and the third register, so the training inputs with the new inputs. And after that, you would apply a conditional measurement. And then in this specific state, because the measurement led to the qubit or the output being to state 0, you have your probability of what if the last register is 0, and then this basically computes, okay, what's the accuracy of the probability of you reaching the class state of -1. And that's after you do your conditional measurement. And then basically how this really works is very similar to the kernel trick method in classical machine learning, where you're just taking in all the average weighted sums of the training inputs, which have heavy weights recorded to them. And as you input a new feature, you measure the squared Euclidean distance between the new data points, and the closer it is to your training label data set, the heavier the weights will be, and giving you a better accuracy. After that, so how do you encode the specific data set or input vectors? So you have, again, the four registers. So first the index register, then the ancilla, and the third register where you put in the class of either +1 or -1. And then this is the specific information you would use on the last register to encode the input vectors. After that, this is what this final circuit looks like. So a lot of it in the beginning, for instance, A, B, C, D, E, is a lot of the state preparation into getting the data or the input vectors into the quantum circuit, and then the last instance F, is actually your classifier. So then as I looked further into the specific classifier, I realized it doesn't work when the data isn't linearly separable. So if you have a data set that looks like this, that's on a 2D plane, non-linear, then the accuracy will just fail and it won't work. So then I started looking into quantum support vector machine kernel algorithms. Basically being able to take non-linear data sets on a 2-dimensional place and using the kernel trick to project the data points into a higher dimension, so you're able to classify them and basically compute the inner product between the two different vectors of the data points. And quantum computers are actually very efficient at doing this, so that's very good, and this works. And so then I ended up implementing this on the IBM Qiskit software, where they actually just simulate the support vector machine algorithm. And I used a specific breast cancer data set to test the accuracy and see how it worked. And they gave me around like 82% accuracy. So it ended up giving me the idea that yes, this can be done, and it could be used for complex data sets that aren't linear on a two-dimensional plane. So as I continue learning about this field, I think the implications are really, really huge. You possibly have the ability to solve really important problems and even make our AI better, machine learning models better, and possibly go towards an area of artificial general intelligence. So my next steps are actually being able to go deeper into this topic, keep learning about the different machine learning models that could be implemented, and doing more experiments and learning. So thank you for your time, and that's the end of my presentation.